This is a joint work with Roy Brooks from Cisco Systems and Nicholas Fischbach from Colt, and actually it's a joint work with Paul Quinn, Andreas Fischbach, Mark Binder, Anat Bremler-Bar, Boaz Elgar, and Roy Hermone. We all worked on those methods that we are going to show now. So actually, you can view this talk. It's a nice next step after the talk of Barry Green and Danny McPherson of yesterday. So when there is a problem with some of your customers, one of the stubs or attached servers, sometimes we use the sinkhole. We advertise the sinkhole address and get this traffic routed to the sinkhole. And in all the methods that we saw yesterday and that are used today with the sinkholes, usually the traffic in the end is get dumped and not used. What we are doing today, we are taking it one extra step, and we are offering to a method by which you can take the traffic and return it to the end, to the intended destination. So there are some applications in which you can apply all kinds of things on the traffic, like sniffing the traffic, doing health check on the traffic, or any cleaning the traffic, filtering traffic, and send the remaining of the traffic or whatever you decide to forward to the intended destination. So you could use it for reverse proxying, for cleaning DDoS traffic, for doing on-demand traffic monitoring or sniffing. So what's the difference between the two methods? The sinkhole is a unidirectional. The traffic only gets in, and in the shunt, the traffic goes in and out. Sinkhole is quite standard to implement just with an IP, standard IP technology. You don't need tunnels. And in the shunt, as we'll see, we use, at least in one of the directions and sometimes in both directions, some form of tunneling, some way of tunneling is a GRE, IP, MPLS, or L2TP version 3. And as we see the applications, in one of them you just black hole DDoS traffic, in another one you can use it to clean the DDoS traffic or to do reverse cache proxying. And one method was already introduced by the UUNet crew in the 17th NANOG. And as I mentioned earlier, the reverse cache proxy by Hardy and Wessels that can be used in the shunt. So the main problem, if I just use the standard techniques and the traffic back, I obviously get into an infinite loop. So we need to do careful traffic routing. One way you could do a tunnel from the peering routers into the sinkhole, but then you have to make sure that the traffic going from the sink back to the intended destination doesn't go through a peering router. Otherwise, we still get into the infinite loop. So you can use a tunnel both directions, both from the peering points into the sink and from the sink to the intended access router into the customer equipment. And as we see it here, there are some implementations with GRE tunnels, but in many cases you face the situation where the GRE tunnels require special hardware, extra cards for the dedicated card for the implementation of the GRE decapsulation or the GRE encapsulation. Usually it's the decapsulation. The encapsulation you can do in the sink itself, and it possesses some processing overheads. So if you happen to have MPLS in your network, you could use one of the methods that we are going to present today. It doesn't require any extra cards, no extra hardware, and it is supported by Juniper and Cisco in recent versions of the operating systems, of the respective operating systems. The requirements that we impose on ourselves when we sit down to design those methods is first that when you want to activate this method, when you decide for a /28 or /32, I want to shunt it, that we will not have to do any dynamic configuration. So when you start the operation of this shunt, it will be without any dynamic configuration. The sync processor will be able to start the operation and the shunt will work. In addition, we require minimal initial configuration. So we don't want to start doing a huge configuration change in the routers and in the backbone in order to enable the method. And it will be nice, although not always necessary, that the sync engine itself will not be speaking MPLS. It will be ignorant, doesn't know anything about MPLS. The backbone itself has to be able to support MPLS, but it has to be MPLS enabled. It doesn't have to run all its traffic MPLS. It could be a network running only IP traffic, no MPLS, and you could use the MPLS only for the shunt if you're using one of our methods. So we are going to show two implementations. The first implementation is based on the MPLS using the proxy egress LSP, which is basically doing a lot of taking extra mileage on the penultimate hopping that we saw in the tutorial on Sunday, actually. And the other method is based on MPLS VPN. So I'm going to turn to Nico. He will tell us about the first method.
We got an MPLS enabled core, and for us it wasn't a solution, to use Jerry and this kind of methods to divert traffic. Basically, since the backbone is MPLS enabled, you probably know that the LSP, the label switch path, is going to follow the IGP information. So in the standard setup, you have one network, which this is like the 61 network reachable over one of the LSPs. And we have the single server standing there with just basic configuration. The boxes is, the only thing we have to do when you want to divert traffic, and this is going to be the minimal configuration change you have to do, is just to announce a new next hop for the prefix you want to divert to the sinkhole box. So when you have this setup, we'll have all the LSPs that will be kind of automatically created when we inject the new next hop, or better said, when you have the route to the loopback, then it's going to hit the IGP. Basically, we do that using ISIS. So you're going to have all the LSPs that will go to the sinkhole. When the traffic is going to enter your network, it will first hit on the left the edge or peering router. And what we're going to do from the sync router or from a router next to it is just announced over an IBGP session, and that is what you will have to do before using the sync, is to configure the BGP sessions between this sync router and all your peers if you run any AnyMesh or with the route reflector, depending on the setup. So we're going to announce a new route, and when the packet's going to enter the network, it's going to be a normal IP packet, and it will be tagged when the IP lookup occurs. So when it enters in the first table, you're going to see the IP is going to be a loopback, and it will be mapped with into a LSP, get labeled and get over an interface, and it will follow the LSP through the network. So you see the different table lookups, packets forwarding, and we will hit the last box. On the last box, we will untag the packet, and it will exceed the LSP and go to the sync router, and as being a normal IP packet. So depending on your setup, if your sync router is speaking LSP, you don't have to untag. You can send a normal IP packet that is labeled to the box and forward it again. In our setup, we decided to untag and to give it to a box that can be running, like I said, DDoS cleaning, a snort, TCP dump, snoop. You can even have a secret cache on it if you'd like, if you want to do some strange tests. So that's the way of doing it. The difference you're going to see in the network is really going to depend on how you do the setup. If your backbone is really MPLS labeled and all the traffic, also normal non-diverted traffic, is going to the backbone, the person or the users won't even see the change. The only change they may see is the delay that may be changing between the hops, because you only see the egress and the ingress boxes, or depending if you propagate or make the network TTL transparent, you won't even see the IP ops in between. You could call that security by obscurity, but that's just kind of for your information. So the last box is the penultimate hop router. Okay, and information about the LSP proxy egress. So how does it look like? So we have the LSP set up, the ones in blue, between all the egress or peering routers going to the sync device, and in purple kind of the link back to the final destination. So via IBGP, we're going to announce the new next hop for the traffic we want to divert, traffic going to 61.1111. And all the traffic entering in red will go over multiple LSPs to the synchronous device, or to the shunt device in our case, for inspection or whatever you're going to decide to do with the traffic. And once done, it will get back to the final destination. Depending on what you do on the device where you divert the traffic to, by default, the outgoing traffic from 61.1.1.1 is going to go back directly and not over your synchronous device. So if you don't use an application level thing to play the kind of man in the middle, the traffic back won't go over the synchronous device. And this is something where I was going to show you how to do that with VRFs, to have in and out going over the same system. So the actual deployments, we have all the LSPs set up to divert the traffic coming from the transit paths that we have going to New York, some of the peering routers sitting in London, and so on. So what you see in London is that the traffic we want to divert enters the box, gets tagged, and the next hop is going to point to the LSP and go to the final destination. And in Frankfurt, the traffic is getting out of the LSP, gets untagged, and the next hop is then the cleaning device. That's 61.44.88.111. So this is just the basic thing that you're going to see. It's kind of easy if you just use MPLS to do that, if your background is not fully MPLS enabled, because your operations guys won't have to learn MPLS, for the day-by-day operations, but only in the case of diverting traffic. What you also see by doing that is that we have less overhead and it works quite stable in a transparent way. So that's basically our experience doing that. We have been running some tests, and we use that setup to do some packet scrubbing, changes, analysis, protection with some of the customers we have in Germany that are like being dosed once a week or 2 times a week. And it's really effective and it works quite well. So that's it. If you have any questions, we can probably take them offline or after the presentation from Roy.
This method is a little different. It requires a little more configuration, but because you're using separate routing tables on the sync router and the egress router, you guarantee you could never have a loop regardless of what BGP routing information you send to the devices. So in this example here, we have VRFs configured on the sync router where the traffic will be returning, as well as the egress router. Now on the egress router, the customer interface is not in a VRF. It's part of a global table. The only interface in the VRF is the loopback in that router. So when we send multi-protocol BGP, VPN, v4 routing information, it has that router as the next hop, and when the packet gets there, the lookup is done on that table only. So you advertise the prefix that you want to clean. The traffic gets sent down to the filtering device. The PE has already been pre-configured with a static route pointing at the customer interface in the VRF for that prefix. So now that's being originated in the VRF. The traffic, when it gets returned from the filtering device, comes into a VRF forwarding interface on that sync router. It's going to see the advertisement, the multi-protocol BGP advertisement, pointing to the next hop of the egress PE and put on a 2-label stack. In this command here, you can see where the routes shows the next hop as well as the 2-label stack that we're going to put on. The top label gets the packet to the egress device. The penultimate hop will pop that off. The bottom label, the VRF label, when it arrives at the egress, the router will look in the routing table for that VRF to determine what to do with the packet, and it will be sent out the customer interface. On the PE device, you can see where we have a static IP route pointing out the VRF. using a global next hop. This is how you connect the VRF to the global routing table. So when it comes in the VRF, it knows to use a global next hop to send it out. And you can also see on the bottom line that there's no tags imposed. This is going out untagged. Well, I put a lot of these in here. If you wanted to do two-way filtering with the VRF, you can do this because you can forward all the traffic back to the sync server. So Cisco has a feature called VRF Select. Juniper also does this, and it's called filter-based forwarding, where anything that matches some filter can be forced to use a VRF routing table. So when the traffic comes in the global interface, it passes the list. If it matches, it sends it on the VRF, and it goes back to the sync server, where then it gets sent through and forwarded back as normal IPv4. The Cisco show command for this is described here. On the VRF, we tell it that we're going to do VRF select source, and then there's the command VRF selection source identifies which source IP addresses to match to send on the VRF. So there are code requirements to do this. To do the MPLS VPN, you need to run 12011 ST or 12022S. In Junos, the requirements are for 5.3 or 5.4. So, the caveats here are, the denial of service or the traffic still goes through the backbone and you're not filtering it at the edge. And there is some latency involved. The latency for the number of hops is usually insignificant. Routers are very fast at this point. It's just really the distance that you're sending the traffic. So for the MPLS VPN, again, there's iOS support issues for your devices, and for the egress proxy LSP. If the egress device and the peering router are the same box, if you didn't use a more specific prefix, you would potentially have a loop. If you had the filtering device on the same box also, they definitely have an issue. So the advantages are that this filtering isn't done in the critical path. It's taken off and sent out. The normal IP traffic wouldn't be affected by this. There's no additional load on the routers. The IP to MPLS or MPLS to MPLS has no detrimental effect. You can have LDP only advertise the prefixes that you want to have labeled traffic sent to. So in this case, only the sinkhole loopback can be advertised by LDP, or in the VRF instance, you would have to use a second loopback interface on the device. Then when the eBGP VPN-v4 message is sent, it has a next hop of the second loopback, and there's a label for those loopbacks only. So simple to deploy and scalable, definitely for the egress LSP, proxy LSP. The MPLS VPN solution is slightly harder, but like I said, because you're actually using separate routing tables, it guarantees a little safety. You can never create a loop that way. So what's next? Distributed sinkholes. There's, that's possible, and you'd have to. You could use either one of these solutions to do that also. Any questions? I'm very surprised. I wasn't sure that MPLS would be received so well.
There are no questions, comments?
Yeah, just one thing. If somebody wants the configuration of both the Synchronous device, the peers, MPLS, and so on, just drop me a mail. I can send them.
Is there somebody doing this?
We are.
We are River
Colt.
Okay. If nobody has any other questions, then I guess we're done. Thanks, you guys.